EET105 inductors, example problem number 26, Thevenin equivalent, where tau equals L divided by RH. So for this network, switch is closed at t equals 0. Part A says determine V sub L at t equal to 25 microseconds. So this looks like a pretty complicated circuit here, right? So the first thing that you're going to need to do is find the Thevenin equivalent for the inductor. So the terminals that you want to label as A and B, or this one, around the inductor. And you can flip positions with R4 too. So you can put the inductor over here and put R4 over here. They're still in parallel. You're not changing the circuit. So they drew that here, and they didn't put their A and B down, but they took the inductor out and they shorted out the voltage source. So that leaves R1 in parallel with R2, as you can see, and then those two guys together are in series with R3, and then those three together are all in parallel with R4. So this is the way they wrote it here. You need to do order of operations, work inside the parenthesis first, and the higher order of operation is the parallel operation. So you do that math and you fill out the values, 8.2 in parallel with the 2.2, and then after you're done calculating that, you add it to the 2.7K, it equals 4.43K, and then this in parallel with the 1K is 1 times this all over 1 plus this, ends up equaling 1.816K. And then the second part of your Thevenin is you put the voltage source back in, and you want to figure out what your voltage is across here. Okay, so now you're looking at RT. RTH was looking from right to left. RT is now looking from this point over RT prime at least. So what you do here is R3 and R4 in series because this is open. Okay, you really need to look at this part of it. This is an open circuit. So you're wanting the voltage across R4 is what you want here. So you calculate RT, which ends up equaling 3 and 4 are in series, and then those two are in parallel with R2, and that's in series with R1. So they did that math, and you end up with 9.58 kiloohms. And then you take I sub S is E divided by RT. 36 divided by 9.58K equals 3.76 milliamps. So then I prime, using the current divider, I sub S is coming into this node here, and it's dividing down into R2, and also dividing across this way through R4 and R3. So the way to do the current divider here is they defined I prime as the current going through here. So it's the resistor in the other leg, which is R2, times I sub S, the current coming into the node, all divided by, this is R2 plus R3 plus R4. Reason why is because you have R2 in this branch, and in the other branch you have R3 and R4 in series, which is these two added together. So you do that math and you end up getting 1.4 milliamps. So E Thevenin is the voltage across R4, which would be I prime times R4, which ends up equaling 1.4 volts. So that was the Thevenin portion of the problem. That's just getting it set up. So now here's your Thevenin circuit, which is E Thevenin in series with R Thevenin. You put the inductor back in, and now your tau equals L divided by R. It's R Thevenin that you put in for R. You calculate that out. Since this is a storage problem, you use the storage equation and you plug in your values In this case, it's going to be E Thevenin you put in for E because you simplified it down to this circuit. And then you plug in your tau here, and the problem asks you find VL at t equal 25 microseconds. So you plug in your 25 microseconds, do the math, you get 180 millivolts. And then part B says find VL at t equal 1 microsecond. So all you do is plug in t equals 1 microsecond here, and you get this result. So part C asks you to calculate V sub R1 at t equals 1 tau, R1 being down here. You have to go through a similar process as what you just did for the inductor. Now, this is your target element. So now you're going to have to find the Thevenin equivalent at this point. All right. So how do you do that? Well, you set up the circuit this way, and what we're looking for is the Thevenin equivalent. So we take, again, our charging equation for V sub L because there is a voltage across it here. And we plug in our E Thevenin, and we plug in for little t, we put in tau. We get 1.4 volts times e to the negative 1, which ends up equaling 515.2 millivolts. So that's like a voltage source right in here. And then this is the Thevenin equivalent. So then you take this circuit, take it out of there, and you short out your voltage sources. So now your R Thevenin is this resistor in parallel with this resistor equals 1.21 kiloohms. And then to get E Thevenin, you plug back in your voltage sources and you do a KVL around the loop. So you get minus E Thevenin plus 36 minus VR2 equals 0. So you find your E Thevenin here equals 36 minus VR2, and you do a voltage divider to find out. You put in the 2.2K times this voltage here divided by these two resistors, which is going to end up being 0.231 volts. So then you plug VR2 back in here, and then you get E7 equals 36 minus 0.231 equals 35.77. So this equation here came from this loop, and then this equation here came from this loop on the right side. So you're looking for the voltage across this resistor coming from this source. So then you combine them both together and you get E Thevenin prime. And then your E Thevenin prime, you plug it back into Thevenin equivalent and you get something that looks like this. We calculated R Thevenin to be 1.21K and your E Thevenin prime to be downward. And the reason why it's downward is because of the polarity that we have selected here. All right, it's going this way. So then you calculate VR1, which is what we were originally asked to calculate, doing again another voltage divider. So it's the 8.2K times the voltage input coming in divided by the sum of the two resistances equals 31.34 volts. And then part D is asking you to find the time required for the current I sub L to reach 1 milliamps. So again, you use your charging equation, your storage equation here, and you plug in E Thevenin and R Thevenin, plug in your values, and this is You don't know what T is. You're looking for what T is, right? It's asking you what is the time required for the current to reach 1 milliamp. So you're given I sub L is equal to 1 milliamp. So you have to set this equation up and fill all the values out and then set I sub L equal to 1 milliamp. And now we have to solve for T. So how do we get T out of there? Well, you simplify this. 1 milliamp divided by 1.72 is 0.581. Simplify it more, you get it down to here, and then you have to take the natural log of both sides. So the ln of 0.419 is negative 0.87, and ln of e to any power is just equal to that power. Okay, so that's the power minus t divided by 12.25 microseconds, and then you multiply both sides by 12.25 micro, and you get 10.66 microseconds. So I drew this circuit and every circuit again, looking for different, the current through and the voltage across the inductor, and then this was what I got. I set my simulation speed to 1 microsecond per second because I knew the tau was roughly around there, or at least one of the taus was. So tau, I said that made a mistake. This is 10 microseconds per second because my initial tau in the problem when we calculated over here was 12.25. So I built this circuit in every circuit, and I'm looking for the current through the capacitor and the voltage across the inductor. So I turn my circuit on, I close the switch, and again, here's what you get. So if I look at this, it has a minimum of 0 amps, a max of 1.71 milliamps, and then this is a minimum of 0 volts that it decays down to, a maximum of 1.35 volts. And if I wanted to look at this variable too, I could turn it on and rewind the circuit, play it, open it up, pause it, rewind it again, and I could turn these two off because they end up interfering with what it looks like. And I could turn it on, turn the circuit on, and that's where the voltage ends up being by 31.4 or so. And that should have been what we calculated. Yeah, here's what we calculated, 31.34.